Okay, in this video, we're going to be taking a list of nodes and edges, specifically one that was generated using the bibliometrics package in R. We're going to take those nodes and edges and inspect the structure of that network using an interactive tool, an interactive app called Gephi. So let me begin with a screen share here. And this is kind of where we left off. In R, we generated an edge file and a nodes file here called CSS nodes text, CSS edges text. The CSS stands for Computational Social Science. So now we're going to open up Gephi, and there it is. And you can see Gephi was developed back in 2008, and it's now 2023, 15 years later, several generations in terms of, I think, most digital applications. And in the course of that time, Gephi has always been finicky. Gephi had kind of went through a latency period in the mid 2010s, and it's lately been kind of resuscitated by the hard work of its authors. So we're going to take Gephi. We begin with a screen that looks something like this. We're going to click on a data laboratory tab. Not much is happening there. Let's try a file import. We're going to import two spreadsheets, and those two spreadsheets are our nodes and text and edges files. I'm going to do the nodes one first here. And we can see we're going to bring this in as a nodes table. Here are the fields that we have. We have a label field corresponding to the short label that we've got for each paper. An ID, a numerical ID beginning with 1 and going up to 794, the total list of nodes. The title of the paper, the journal of the paper. This is the short name for the journal. Let's see if we can open that up. That's what that looks like. And then I've got a field called all text, and it's really not all text. It's not the whole text of the paper. What it is a concatenation of the title field, the abstract field, and the keywords fields. There are two keywords fields. One is the keywords that are generated by the authors, and the second is the keywords that are generated automatically based on an intelligent analysis of the paper structure. I think keywords are problematic as labels for papers, because I know that I don't think we're not all working from the same information or with the same diligence when we assign keywords. So if we wanted to study a network based on the text of a paper, ideally we'd have the whole paper, and we can do that. But here we're just working with the paper's metadata, and that metadata, it doesn't include the whole text of the paper, but it does include the abstract. So this is all of the text that we have available. So that's our nodes file, and we're going to save that nodes file as an undirected network, because what we're going to be concerned with is not the act of citing that paper A in 2022 cited paper B in 2016, but rather something which is more reciprocal, that is an index of the number of shared papers that two papers, shared references that two papers have in common. So we'll see that shortly. This undirected network consisting of these nearly 800 nodes. And is that a network? Well, kind of. it is a network which is completely unconnected. It looks like this, a bunch of dots that will magically appear once it's done initializing. And if you have nothing else to do, by all means, count those dots and see if you can get 794. As an aside, that is a great exercise for social psychologists if you're interested in something like a minimal group example, but that's an aside. Okay, so our data laboratory at this point, it consists only of nodes, but let's connect those nodes with our edges. And our edges have, they have source and target identified in terms of these ID fields, okay? And the weight, that is the proportion of shared references. Now, source and target in this undirected network are kind of, they're arbitrary terms, but we need to use both for Gephi to cooperate. And for Gephi to cooperate, we need to be kind of careful here because Gephi's defaults can't be trusted. This is an undirected network, but it comes up as a directed one, so we're going to change that. And when we shift from directed, where it thinks there are 60,000 references, to undirected, where it recognizes that there are 30,000 edges, the directed network includes both halves of this kind of this bidirectional arrow, if you will. We want to represent this as undirected. And critically, we want to append this to our existing set of nodes rather than construct a new workspace. So it gets rid of the duplicate edges. That's all good. And now what does our network look like? It looks like, if you are into Italian food, you might be familiar with pasta, black pasta made with squid ink. Here it is on a square plate, a plate of square pasta. And we're going to kind of, we're going to change this into something which is coherent. So that's our objective. But we're going to proceed first by looking at some characteristics of this network. The first is the average degree, the average number of papers to which a given paper is linked to, and that's 76 out of 794, suggesting a graph density that is about 10%, and sure enough, that's what we get here. When we look at the weighted degree, that is the average proportion of links, proportion of shared references for the for those links, we see it's about 4%. When we look at the network diameter, this is going to describe the distance between any two nodes in this network. And we're looking at, if we look at the overall diameter, that's the distance between the two farthest nodes. And then we're going to get an index of the average. So the diameter of the net is 5, and the average path length is 2. Now, in a sense, those things aren't strictly true because this network is not completely connected. It turns out that there are some papers that are separate from this network, and we can see those here, for example, where we look at connected components, and we see that there are 23 connected components. And what I want to do is I want to get rid of the 22 smallest of those, and that's going to be our first attempt to kind of parse this network. That those 23 connected components, there's one big one and 22 that are disconnected. And so what we're going to do here is we're going to filter out the filter this network based on this giant component. And we could do this, we're going to keep the papers that are in that giant component. And when we do this, we go from a network of 794 nodes and 30,194 edges down to a network with 22 fewer nodes, yet the same number of edges. So we've got 22 papers that are out separate from this. And the thing is, that shouldn't really be there if we were looking at a network of this size. I'd expect everything to be connected. But it's arisen in part because we didn't carefully filter our papers. For example, if we had selected only papers that were research papers or reviews, and if we had filtered out editorial matter, excuse me, then these 22 papers might have disappeared. But we're going to drop them here. We're going to do some more filtering, and we're going to make this network somewhat coherent. We could begin by doing a modularity analysis of this connected space. And when we do that, we get 7 communities. And these 7 communities, there are a number of ways. Okay, so very brief digression. If we think about a network like this one, and if we think about these nodes as being like stars in space, then it's any way we draw lines to delineate communities in this space, it might seem kind of arbitrary, and it often is. So there are a number of algorithms that we could use to isolate clusters or communities in this space, in the night sky. And the one that is used by Gephi is, I think it is a version of the Leiden, L-E-I-D-E-N algorithm. And it's a little bit dependent upon the random seed that it begins with. So if I was to run this again, remember we got 7 communities here. I'm going to run this a second time, see if we get the same result. I get again 7 with a modularity of 0.33. Let's try one more time here. Okay, so modularity of 0.332 and 7. So the point that I'm trying to establish here is, but failing to establish, is that the results aren't 100% reproducible. Okay, here we get 6 communities instead. So, one way to do this is to do it a whole bunch of times. Here we get 8. Let's work with 8, what the heck? And see where we go with that. Actually, I'll do it one more time because that's kind of, let's go back to 7. There we go. Okay, so we have our 7 communities. Some communities, let's, what we're going to do is we're going to paint this first. Let's paint this by our communities. Okay, so the question, again, the modularity algorithm in Gephi, it's not ideal because of this dependency upon the initial random seed. There are other approaches. If we identify communities within R, we might get results. We will get results that are more reproducible, okay, because we can use a set seed command, for example, and then use the same algorithm. Okay, so our modularity class analysis, we've got one tiny modularity class and 2 small ones and 4 that are bigger. And now we've painted the network using these colors. We can see, this is kind of cool, actually. We can see that there's this one very dense area in cluster 1 and so forth. And our plate of squid spaghetti is now a plate of not tricolor spaghetti, but something more exotic. We could try generating, what we're going to do now is we're going to attempt to make these communities more homogeneous. And we're going to do so we can think about nodes as kind of having a gravitational force on each other. We could think of these edges as springs which vary in diameter or corresponding to the weight. And what these algorithms, the layout algorithms, are going to do is they're going to collapse this network as much as possible. And the result is going to be a space in which colors are painted a little bit more homogeneously. Now, when I use the force atlas algorithm, it's happening pretty slowly here. And I'm gonna spare you. So let's try a different algorithm. Let's try okay, there we go. Let's try Force Atlas 2. That might be faster. And if that fails, then we could try Fruchterman and Rheingold. Okay, so that seems to work a little bit better, a little bit faster. And we can see instantly we've got this space suitable for framing, but not really suitable for understanding. And I'm going to stop this because it's still kind of sorting. But we can see we've got this pinkish purple community here, consisting of 30% of the nodes, green, again, about 30%, and blue, about 26%, and then orange over here, 10%, and we've got some strays. Those are our gray ones and so forth. Now, we don't really know what's going on here, except that computational social science appears, if we take this at face value, to include these 4 things that we don't yet understand. So let's try to understand these. And we're going to try to understand these by filtering out based on the some characteristics of the nodes. And what I want to do is I want to pull out the most central nodes in this in the network. And so I'm going to use PageRank. I'm fond of PageRank because it's recursive and clever. In the PageRank algorithm, here it says it ranks pages according to how often a user following links will non-randomly reach the node page. That's kind of one take. Another take is that a node is central to the extent that the nodes to which it connects are also central. So when you get to a central node, you're going to be progressively likely to connect onto these more central nodes. Now, PageRank, it's so clever that it actually was the initial model for the Google search algorithm to determine the order of web pages. And because of that, we might think that that PageRank is based on this kind of notion of web pages, and it is, but not because of the word web page, but because of the founder of Google, who, of course, one of the founders was Larry Page. The other one was Sergey Brin, but we don't call it BrinRank or web Brins. Okay, so now we have this measure of centrality called PageRank. And what I want to do is I'm going to sort these nodes. Remember, I previously removed papers that weren't in the giant component. Now I'm going to remove nodes that have low page ranks. So I'm going to drag this down here, and we're just going to kind of arbitrarily set some value here. And we can see now we've got a network that looks kind of like this, a network in which there are 30 nodes and 400 edges. Okay, that's fine. Let's take a look at those. We can inspect the labels for these nodes. Excuse me. I'm going to have to highlight my assign labels to my nodes, and we can see we've got those here. Let's make those labels for the nodes a little bigger. No, that didn't do it. This one will. Let's get rid of boldface because we don't need bold. Okay. And we can do a sorting of this again, just based on the visual chart. And I'm going to weaken the gravity between these nodes, 0.1. That didn't seem to do much. We want to kind of tease these suckers apart a little bit. Approximate repulsion, scaling, stronger gravity. Let's see. Well, there are a number of ways you could do this. Edge weight influence. Let's try that the other way. No. Okay. All right. So we can work with this. Let's make those guys a little smaller. Okay, we've got something looking like a net, not a net as in Funicello, the Surf Queen, but this we've got a network consisting of these four areas are all represented. We've got these individual papers. I'm going to apply a second algorithm, and I'm just going to make this a little bit prettier, and then we're going to kind of move on. Okay, I'm going to adjust the labels to kind of separate them. You can see that that's okay. I could do something that I'm ambivalent about, and that is I'm going to kind of pull a few nodes closer together. And part of the reason I'm ambivalent about it is that as soon as I've done that, I've made my work even less reproducible. I'm no longer working with simply the force atlas and label adjust algorithms, but I'm working with Lanning's manual tweaking of the network. Okay, so we can't really see a lot here. We can see some, but we can see it better if I click on the preview tab, which I'm going to do here. Again, I'm going to show those labels. I'm going to make the labels a little smaller. And let's make the label smaller still. Okay. We can see that here, unlike in the overview tab, we can't tweak the position of individual nodes, but I don't care that much. This is kind of giving us this initial understanding of what things look like. I want to make the edges a little bit darker here, so let's do that. Okay, and suddenly we see that some of these appear to be more closely connected than others. I want to do what else? I want to set the outline color to white, basically, to make this nicer looking, but that's just me. And the point is that we could save this as a picture, and ultimately we might want to do that as PDF or whatever. But the question is, what are these networks? Or excuse me, what are these communities that we've identified? We have these four communities, and if we know what these papers are, and I don't offhand, I know that Michal Kaczynski's got a review paper, and that's probably what that is. We've got well, gee whiz, I don't know what these individual papers are. How do we identify these communities? Well, for that, we're going to go back into R, and what we're going to do is we're going to take not just these communities, but are not just these individual nodes, but we're going to look at everything and this whole network and identify the characteristics of each of these communities based on that text field that we've got. So in order to do that, go back to our data laboratory. We're going to export our nodes, okay, our node list, and let's go ahead and do that. And we'll do that, we'll call it okay, and so with that node list, we're going to go back to R, and then we're going to do some real rudimentary text analysis. And I'm going to have that in the third of these videos. So